Welcome back to Hands-On with Reinforcement Learning. In this section, we're looking at the Contextual Bandit, which is the stateful, more complicated version of Multi-Armed Bandit. In this video, we're going to combine the agents that were written in the last video and the Contextual Bandit environments that we wrote in the first video, and we perform the training step to understand that A, we're going to actually train the agents successfully, and B, we're going to actually train it to learn the best policy. Specifically, we want to also compare the training loops of Multi-Armed Bandit against the training loop of Contextual Bandit. The second thing we're going to do is to implement the training loop and run it to understand that we have successfully taught the agents something, and that it taught itself the best policy to crack the Contextual Bandit environment. In the last part of this tutorial on Contextual Bandits, let's again go through what we've done for the training loop for the Multi-Armed Bandit environment and import it over to the Contextual Bandit environment so that we can have the same thing. Let's go back to multiarmbandit.py and have a look at what the training loop looks like. It's very simple. We create the environment, create the agent, we decide how many episodes to run this on, and we create a variable that holds epsilon, which is used in our epsilon exploration strategy. We create a new session, and for the episodes in all the episodes that we decide to run, we ask the agents to find a new action, whether that's a random action for exploration or a predicted best action for exploitation. We look at what reward results from the action, and then we train the agents to recognize what actions produce what rewards, so that it could better predict what's the best action given the Multi-Armed Bandit that we're looking at. Now let's look at how we do this for the Contextual Bandits. Again, we create the Contextual Bandit environment, create the agents that we have coded up in the last video. We create the number episodes variable and create the epsilon variable. We start a new session that allocates hardware resources to TensorFlow. We initialize all the variables that we're going to use in the graph inside the agent. We run a loop over all the episodes we want to use for this Contextual Bandit exercise. We find the state of the environment by calling environment.getBandit, and then we store it in context. Using this context, we ask the agents to predict the best action for the current episode. We execute that action on the environment, and we get back the reward. Taking all these new information, we're going to feed it all the way back into the agent and train it. Normally, we stop here. So if you look at our multiarmbandit.py, we have stopped here. But because Contextual Bandit is significantly more complicated, I've added some code here where it says if the number of episodes we're on is an index of a multiple of 500, we're actually going to run the loss of the agent. And this loss here is ran the same way that the train function is constructed. So I encourage you to take a look at the code later after you have followed this tutorial and coded it up yourself, why we're creating and running the loss function like this. Given that we have retrieved and calculated the loss, we can then print it out and say in the step 500 or 1000 or 1500, the loss is like this. And if we have set up the agents correctly, we should see that the loss stochastically tends towards 0 as we train it through more and more episodes. At the very end, we're going to print out the results. So we're first going to find out, given different bandits, what's the best action. So we're using the function argminimum and run it through environment.bandits, which is the weight matrix, as we can see here, that defines the reward thresholds for different bandits and their actions. We then comparatively print what the agent predicts is the best arm for the first bandit. We'll repeat over the other two bandits. So there we have it. So let's go into a terminal and run this and see what happens. So now I'm back in my terminal, and now let's run that script. So we have Python, and then we run the script. So as you can see here, we're rapidly going through all the episodes, and as we've configured, every 500 steps, the loss is printed out. And we can see that the loss, by and large, is tending towards 0. It's getting smaller and smaller. You can see here, this is 0.002, and in here we're 0.005. You might also notice that sometimes it kind of like flares up into bigger numbers. And that's actually fairly common in training a neural network because of how many batches of experiences are fed through, and therefore the randomness of the training data sometimes will flare up the loss. But as long as the loss overall is tending towards 0, we should be fine. In fact, if we look at the last, 3,500 steps, actually the loss is very nice and tidy, very, very close to 0. Best of all, as you can see at the end of the 30,000 training steps, we actually see that the best arms, as dictated by a weight matrix in the environment, actually corresponds to the best arm that the agents have learned. So there we have it. We have constructed a contextual bandit environment. We constructed an agent that could take the context and learn that, given a context, what's the best action to execute. Now we created a training loop that is very much like the multi-arm bandit training loop that we had, but instead also takes into account of the context. And we have shown that we can train this efficiently. Great. So that was very fruitful. So let's summarize this section. In this section, we've created an environment with multiple bandits using Python and NumPy. In more formal terms, we've introduced states into an environment over and above the multi-arm bandit environments that we worked with in the last section. To that, we then created our first policy gradient-based reinforcement learning agent with TensorFlow that allowed us to learn what state corresponded to what's best actions to produce the best reward. Finally, we built on the training loop from the last section to build a training loop for this section that trains the agent, allows it to learn, and allowed it to learn the right thing. In the next section, we're going to bring it up a notch. We're going to talk about dynamic programming, which is a core concept within reinforcement learning. Dynamic programming has a lot of applications. You might have seen it in some of your computer science classes if you took that. This dynamic programming is actually slightly different applied slightly differently than the dynamic programming you see in coding challenges. So here, it talks about terms like prediction and control and value approximation, and really all different methods of how you can train your agents to understand its environment and come up with the best policy to maximize long reward.